I want to show you what I've been working on for the past 2 days or so. This is called the MLVM, the Modular Limited Virtual Machine. It's called modular because the idea is it's just a simulated bus that you could hook up any given number of components to, and then it would just clock all of them. So let's go to the bus, and the first things you can notice is that it has 16 address lines and 8 data lines, and then one intent line, which can either be read or write. So this just bus just clocks. It simulates the positive and negative edge of the clock, and then it will latch the data on the lines and make it be available to any number of devices we choose to connect to the bus. So we can first look at how I'm using it. So I just instantiate the bus here, and then I start attaching some devices. So I make a RAM, which is a read-write memory, and then I attach a ROM, which is just a read-only memory. And this RAM starts at address 0 and it's 24K, and this ROM starts at address 8000 hex and is 32K. So what this memory does is it just looks for clocks on the pulse, and if it receives a negative clock, it looks if the bus address is in the address range of this device, and then it checks for the intent on the bus. So if the intent is to read, it will respond on the bus with whatever data is at that address, and if the intent is to write, it will simply write the bus data into the memory. And of course, for a read-only memory, we only respond to reads. We would never respond to writes in that address range. So with those two components attached, we can actually turn this on and we can just run it. And right now the bus is running. Of course, it's not doing anything because we just have two memories attached and they don't really do anything on their own. So we can also attach a processor. So this processor is defined right here, and right off the bat you can see it has a bunch of registers. It's got program counter, which is 16-bit, and it's got a bunch of 8-bit registers, A, B, and C, which are just util. Then L and H make up the D register together, so this is the low byte and the high byte of the D register. Then we have the CPU status register and the stack pointer register. So the CPU, what it does is, well, on the reset, it reads from the bus the program counter. So ideally on the first clock, the first positive clock that is, there would already be an instruction on the bus. So on the positive clock, the CPU checks if it has a current instruction it's running. If it doesn't, it checks the bus data and then it selects a new instruction. And then it will basically start every clock cycle. It'll start going through the steps of that instruction because most instructions take more than one clock cycle. And then when we finish that instruction, we set the current instruction to none. And if we have finished an instruction at the end of a clock, we just increment the program counter and then read the next program counter. So this happens on the positive edge of the clock, and we read this program counter, and the memory will respond with the next instruction on the negative edge of the clock here. So by the time the processor gets the next positive edge of the clock, it will already be in this data function latched by the bus. So let's check out the instructions. So I have a lot of instructions here. I've basically designed my entire own architecture, but let's just look at a couple of them. So right off the bat, we have immediate loads. So LNA stands for load next A. It'll just load the next byte into the A register. So how I implement these instructions is that I just have a list of lambdas and iterate through this list as each clock cycle. So this specific instruction would take 2 clocks. And on the first clock, what it does is it increments the program counter and then tries to read the program counter from the bus. And then, of course, it has to wait for that data to actually become available on the bus. So on the next cycle, we actually set the A register to whatever data has been latched on the bus because the memory will have responded on the negative edge of the clock. So yeah, we have load next A, load next B, load next C, and then load next low, load next high, and then this load next D just loads the next 2 bytes into the low and high register as one instruction. And then this does the same thing, but for A and B. So register A is essentially register E is essentially register A and B put together. And yeah, then we have a bunch of other instructions that will just like set registers to another register's value. And then we have some writing to memory. So if I want to write the A register to some address, I take whatever address is in the D register and I put that on the address lines, and then on the data lines, I put the value in the A register, and then this write function is on the bus, and let's see, where is that? Right here, and it sets the intent to write. So then you can check out where the processor actually starts. So the program counter starts on this ROM start, which is at 8000 hex. So we would basically start executing instructions at the start of the ROM. And let's actually load a ROM now. So I actually already have this file that basically just loads a bin file into the read-only memory here. Resets the bus, and then starts taking the bus in a while loop. And I have this rom.bin here, so we can open this in a hex editor and check it out. And we have a few instructions here, so we can get up our instructions file and this rom.bin. And we can kind of get an idea of what's going on here. So first instruction, load next A. So if we look here, we're loading a 1 into the A register. And then next you can see this would load a 1 into the B register. And then we're doing instruction hex 44, which is an add instruction. So this instruction adds A and B and then puts the result into C, and then we'll set the carry bit on the status register if it overflows. Otherwise, it clears the carry bit. And then we have instruction 15, which is load next 2 bytes into the D register. And we can see that the next 2 bytes are 0010, and this is little endian, so it would actually be hex 1000 that we're loading into the D register. And then there's instruction hex 32, which would be a write C. So we are writing the value of the C register, which would have been A plus B from the add instruction, to the address 1000. And then finally we have an EO instruction, which is just a halt. So we can actually run this and watch the CPU perform it. So I will say, just call Python with main.py, and that will load the ROM and start executing. And I have some debug prints set up here and a sleep, so we can actually see what the CPU is doing here. All right, so there is our full program, and we can check out what was going on. So first we read our load next A instruction, and then that instruction reads the next byte. It's a 1. Then we have the load next B instruction, that reads a 1. Then we run the add instruction, which takes 1 clock. Then we have the load next D, and that instruction reads the next 2 bytes, so little endian hex 1000. And then we have our store instruction, essentially. And you can see that this instruction actually sets the intent to 1 because it's writing to the bus. So theoretically, we would have written a 2 to hex 1000 in the RAM, and that would just be there. And then, of course, there's the halt at the end. So it's a bit cumbersome to just type out these bytes and then kind of decipher what's going on. So I wrote an assembler for this instruction set. So here we have an assembler in about just 100 lines of Python, basically. Actually fairly functional for the amount of code that went into it. And then I've written my own assembly language that we can assemble with this assembler. So here is that ROM in that assembly language. So it's very lenient with how you actually store the bytes. So I just put them all in one line like this. So it's just putting the addresses in order. And then, yeah, that's exactly what that last program just was. I actually generated that bin file with this assembler. So we can actually move on to a more complicated program. So obviously the next step we'd want to do is something like Fibonacci. So here is my Fibonacci program. And you can already see we're using a lot more of the features of the assembler that I made. Like we have labels, we have directives here. So, and oh yeah, we have comments and all of that. So I can step through it. Offset 8000 hex basically means that this ROM will be starting at 8000 hex, so that like any addressing would like that's basically to help labels out, so labels know like where they're starting, because this label would normally think it's just at 0, but since the ROM starts at 8000 hex, this label needs to actually be at 8000 hex. So if we ever jump to this label, the CPU knows where to jump. So this says that the ROM starts at 8000 hex, and then this seek command actually sets like the current position to 8000 hex. So if I did like a seek 9000, it would just fill in zeros until we got to 9000, and then this start label would be at 9000 hex. So yeah, the start label here, and then we're loading 1, 1 into A and B. The comments kind of explain what's going on here. And then we have a loop here. So DLA is an instruction that basically just does a print. It just prints the A register. It's just a nice thing for debugging. And then, where were we? We're adding A and B into C. And then we check if the carry bit is set, because that means we overflowed. And if it is, we are loading this label into the D register, and then we are jumping to it if the carry bit is set. JSC is jump if the carry bit is set instruction. And then obviously B equals A equals C, your basic Fibonacci stuff, and then we're loading the loop label into the address register and then jumping to it. So we can actually assemble this. So I will type out the command. And then you say the output file, and it will show you all of the bytes it generated. And I'm not going to step through this all, but you can kind of tell that it's basically just this. Like, you can see the halt at the end. You can see the L and E instruction at the beginning here. So let's just run that like we did before. And you can see it is stepping through it. And we have our debug logs. And it should, when it gets to 233 or whatever the carry bit on the status register is set, you can see that S equals 0x2 after this add instruction. That's 0x2 is the carry bit. So then the JSC instruction knows to jump to halt, and we reach the halt. So yeah, that's pretty nice. The assembler just kind of handles labels. You can put labels like after when you use them, and it will just go back and fill them in later. So I think even in this program, like I defined the halt label after I actually use it. So it'll actually parse the entire file for labels first, and then fill them in afterwards once it realizes what address like the label actually exists at. Right, so that's cool, but we can do some more stuff. So I actually decided I wanted to do subroutines, and so I implemented an entire instruction set for everything stack related. So we have pushing to the stack, we have pulling from the stack, and then we have subroutines. So obviously a subroutine is basically just storing the current program counter on the stack. So I'm writing to memory where I have the stack defined as. I think the stack is just at memory address 0, and then it grows from there. And then I just write the program counter. I write the program counter to the bus, and then I just execute the jump. And then I also have like subroutine if the carry bit is set, and then obviously when you have a subroutine, you need the return function. So this return function just pulls those two things off the stack, then jumps to what you pulled off the stack. Basic subroutine and return. So we can go to my subroutine MLVM file, and you can see it's exactly the same thing, except I put this log into a subroutine, so we can actually see what's happening there. And then I load, oh, and also you can see that I am using this label in the subroutine up here. So I'm loading the address of the subroutine, and then I'm jumping to it, and it will call this log instruction, and then it will call the return, pull off the stack, and then ideally we end up right here on the next line after the subroutine. So I can assemble that. And then run it. And you can see that It's taking a few more instructions to actually output, but if I stop it, you should be able to see, let's see, what is our subroutine instruction? GX52. Yeah, so here is where we're actually calling the subroutine, and then here we push onto the stack, and that is, we're pushing the lower byte of the address here, and then here we're pushing the higher byte of the address, and then the jump actually happens here. So we jumped to the label here. And then the return brings us back to 8006, but it adds 1 since we want to go to the next instruction. So this is where we actually hit the return instruction here. So yeah, we have fully functional stack, fully functional subroutines. So I decided, let's make some more components that we can hook up to the bus. So I decided I wanted to add a peripheral system where I can hook up any number of components that all just have like a few registers that can be written to, and then they handle their own memory, or they handle whatever they need to do on their own, and just have like a unified SPI protocol to them, basically. So we have a 2K block in the address range just for peripherals, and then each peripheral gets 0x80 bytes of registers that it can possibly listen on. So the first peripheral I made was this video card. So it has a few registers it listens on. So it has X register, a Y register, a color register, and then a flip register. And these peripherals basically work in exactly the same way the memory from before worked. They just see if something is in their address range and the intent is right, and then it unoffsets the address. So it basically subtracts the start address of this peripheral from the address on the bus to get whatever register that we're writing to. So yeah, we can write where we want the X position of the pixel to be. We can write where we want the Y position of the pixel to be. Then we can write the color. For 8-bit color, I did like a sort of modified HSV sort of thing because I couldn't find an elegant way to do RGB in 1 byte. So there's my function to convert that HSV byte into RGB here. It's all right. And then on these registers, the register flip actually takes all of the pixels that we have set when we pass in the color, and it draws them out. So that's basically saying the frame is ready, we can present it now. And when you write to the color register, that's the thing that actually sets the value in the video RAM here. So we can use it in the same way that we interact with the memory by essentially, if we go into my video.mlvm here, we have, well, actually there's some new features here. We have all of these sets at the top. I added a set directive, so we can basically have macros defined here. So these variables can be used later in the program. So I'm defining the addresses to interact with all of these registers on the video peripheral here. And then I'm defining some other things like video width and video height. And then these are some addresses of some variables that I want to use in memory. So this is a fairly complicated program. It does a lot of stuff, and it has a bunch of subroutines, and it has subroutines calling subroutines, actually. But the important stuff is this line here, where we load this variable x from memory, and then we write it into the x position register on the video card. So this basically says I intend to write a pixel at this X position, and then I intend the Y position to be at whatever I read from this memory address. And then I also implemented this random instruction. So we're kind of just assuming that the CPU has some sort of submodule that can generate some random byte. And whenever you call this instruction, it'll put that random byte into the A register. So we load a random byte, and that is our color, and then we write that color into the color register. So what I'm specifically doing here is I'm loading the color register, which is 6003, into my address register, and then I'm writing the A register to that address register. And of course, this R&D puts that to the A register. And then I am incrementing my position. So I want to like write to every pixel on the screen. So I have to implement increment X and increment Y. So here's my increment X. I just load X into the A register, load 1 into the B register, call an add, and then set A to C. And then write X back into memory. So I'm writing A back into the address X. And then this is checking if X has reached 64, because since the screen is 64 by 64, if X reached 64, then we're at the edge of the screen. So since X is in the A register, I'm going to load the video horizontal size into the B register, which is 64, and then run a comparison. And compare instruction, where is it? That just compares A and B, and if they're equal, it sets the carry bit on the status register. So if I go back to here, I have this subroutine reset X, and I jump to that subroutine if the carry bit is set. So I'm jumping there if X equals 64. And what that does is essentially resets X back to 0 and writes that back into memory. It increments Y by 1. Since we've written an entire row, we want to move on to the next row. So that's what that is doing. And then we also want to check if Y has reached the bottom of the screen. So we have another subroutine for resetting Y. We do this exact same comparison that we did before, then jump to that subroutine, and then write the new value of Y back into memory. And then for every row, I want to actually update the screen. So I am loading the, I'm actually calling a subroutine here. So I'm loading this subroutine into the address register, then jumping to it. And what this subroutine does here is it just loads a 1 into the A register and then writes that 1 into the flip register of the video card. And that flip register on the video card operates, just if it's written to at all, it flips the video and just displays whatever was stored. So I can compile this, sorry, not compile, I can assemble this. So I will do that, and it's going to be a rather long program. There's all of the hex there, and then I can run it. And I actually didn't hook up the video peripheral, so it doesn't open anything up there. So the program still works, but nothing is like responding to those registers being written because nothing's listening on the bus there. So I can just uncomment this line to attach the GPU that I made, and then run it again, and it opens up this screen. But it's going to take a while for us to see anything because it's not going to update until we've like actually written this full first row, and that's going to be a lot of instructions, and we're only running instructions at 10 Hz right now. So I'm going to go ahead and comment out these lines, and we'll see how fast we can actually have it run. So we should just see it writing rows of random colors if I write this, and it'll actually show you what the frequency of the clock is when I run it here. So there we go. See that it is writing those rows indeed, and we're writing it at about 1.4 megahertz, which is pretty good for like unoptimized Python code. I mean, I wouldn't like beg for much more from Python. And let's see, let me change the program just to show that I can do that. Instead of flipping on every single row, we will flip on every single full screen. So whenever the Y register reaches the bottom, that means we've written an entire screen's worth. Then we'll actually update. So instead of like seeing the row cascade down, you'll just see it change frame by frame. So, oh, I forgot to assemble it. So run the assembler. That is the wrong file. There we go. And then, yeah, you can see that it is no longer cascading down. It is instead flipping. And looks like we're running at quite a higher frequency now, probably because those flips take quite a bit of time. I probably need to optimize that. But anyway, yeah, that is all I have so far. I think it's a pretty cool project. I intend to work on it a lot more. I think it's a nice hobby project. It's great for, I don't know, thinking about new problems that you could possibly have and then just solving them. I don't know. I made this entire video card thing in like an hour and a half. It's pretty fun. And then the rest of it, I don't know, I've worked about 5 hours on this whole thing so far. Probably the hardest thing to write, honestly, was the assembler, but it's not great code. Like, it works. It's really nice, like all the functionality that it has in just like 100 lines of Python. Anyway, yeah, that is my initial update for the progress of MLVM.